So everything we learned so far with the principal energy levels, the sub-levels, and the atomic orbitals, it comes down to writing something called electron configuration. Electron configuration is the arrangement of electrons in atomic orbitals without drawing any diagrams, but just writing it out. Each atom has its own unique electron configuration. So let's get into it. Let's learn how to write those. There are going to be a few details we have to make sure we follow. The principles, there are three of them actually. The Aufbau principle, the Pauli exclusion principle, and the Hund's rule. Those three put together enable us to make sure we don't make any mistake in writing the electron configuration for any given atom. The Aufbau principle helps determine the electron configuration. Electrons fill the lowest energy orbital that is available first. And we already kind of addressed it. So when we say that S subshell is lower in energy than P, followed by D, followed by F, when we are going to fill up the space available for electrons, if we have S available, we will not put an electron in P. Now we can have how many electrons in S? Two of them. So when we are filling up the subshells S, P, D and F for, let's say, n equals to 4, where all 4 subshells are available, we cannot start arbitrarily anywhere we want, such as D or F or P or anywhere. We must first completely, fully fill the S subshell, the S orbital, and then fill the P orbital with all the 6 electrons, followed by the D orbital with all the 10, and then the F with the 14. So that's the Aufbau principle. The Pauli exclusion principle tells us that each orbital can hold up to 2 electrons with their spins in opposite directions. This principle also we have addressed indirectly when we said that each orbital can have 2 electrons. But now we are specifying that the reason is that each of those electron can have opposite spins in opposite directions. Think of how our planet spins. It spins from west to east. That's why the sun rises in the east. It doesn't spin from east to west. And so similarly, there is a spin associated with electrons as well. Not something we have discussed, neither will we, but it could be one of the two. And the 2 electrons that occupy any given orbital, because an orbital can have only 2 electrons, they must both have opposite spins. They cannot have the same spin. Finally, Hund's rule. Each orbital in a subshell is half filled with 1 electron before any orbital becomes completely filled with 2 electrons. What does that mean? If we go back and we see these 4 subshells, S only has 1 orbital, and it must be filled half before we fill it completely, so it doesn't matter. We fill the 2 electrons, but P has 3 orbitals, and let's say I have 6 electrons. Should I fill the first one with 2, then the second one with 2, and the third one with 2? No. We must fill in each one half. So 1 electron in the first one, then another electron in the second one, then third electron in the third one, then come back to the first one and fill up the next electron in the first one with the opposite spin, and then the second one with the opposite spin as well, and the last one then. That's how we fill up each of the orbitals. And just to make sure that I fully spoke about this, the half filling of the orbitals that we do must all have the same spin as well. So the P subshell has 3 orbitals. When we have 3 electrons and we fill up each of the 3 orbitals with 1 electron, each of the 3 electrons must have the same spin in the same direction. Then we come back and fill up the 3 orbitals again with the opposing spins for all 3 orbitals. Sometimes when we want to show the actual way we are filling up, that's when we draw something called orbital diagrams, which are just boxes, and we show electrons as arrows. So for example, one has only 1 orbital, so shown here as a box, and within that you can have 2 electrons, but here we are showing 1. Now how would I show the next electron? For the next, if it was a helium atom with 2 electrons, the next electron would also go here because each orbital can have two electrons. Would it have the up arrow or the down arrow? If you said the down arrow, you are right, because they must show opposing spins, and we show opposing spins using arrows by pointing them in the opposing directions. The filling order is very simple. S before the P, then D, then F. But there are some exceptions as we go forward, and that's why using this graph here will help you to know exactly what gets filled before what. So 1s is filled first, followed by 2s, followed by 2p, followed by 3s, followed by 3p, followed by, you may have thought 3d, but here is the exception, 4s, followed by 3d, then 4p, then 5s, then 4d, then 5p, then 6s. By the time we reach 6s, we are almost at the end of the periodic table, and will not be considering any atoms beyond that, because we will have assigned most of the electrons. If you notice, you can make this graph yourself. You write down 1s, 2s, 3s, 4s, 5s, 6s in a straight line going up. Similarly, write down starting with 2p in the same line as the 2s, going up 2p, 3p, 4p, 5p. Then here, starting with the 3s line, write down 3d and 4d. And the zigzag path, the curved path, is what we take going up to fill up all the electrons. Remember that s orbital sublevel has only one orbital, can hold 2 electrons, p can have 3 orbitals for a total of 6, and d can have 5 for a total of 10. F, not mentioned here, can have 14 because there are 7 orbitals. And here is an example of an electron configuration together with the orbital diagram for hydrogen and lithium. Hydrogen has only one electron, and here is where we write down the electron configuration for hydrogen. 1s1. The 1 here is the principal energy level, s here is the subshell, and this 1 as a superscript represents that one electron that hydrogen has. And here is the orbital diagram for hydrogen with its 1s electron. Now for lithium, lithium has 3 electrons, so its electron configuration is 1s2, 2s1, the 2 electrons here and the 1 electron here for a total of 3. We fill up the s orbital fully. It has only one orbital, the s subshell, that is, and that's the 2 electrons we can have there. Then the n equals to 2, starting with s subshell, can have 2 electrons, but we only need 1 because there are a total of 3 electrons in lithium. Here is the orbital diagram of lithium. The 1s with the opposing spins and the 2s with just 1 electron. Here are some atoms, and try to write down their electron configurations. Beryllium, nitrogen, sodium, chlorine, and silver.